Hi, welcome to another video for organic chemistry. In this video, we're going to talk about oxymercuration and demercuration reactions. So protonation of an alkene leads to carbocations. Acid catalyzed hydration is an inefficient method because of the production of the carbocations. Sometimes when you're producing carbocations, it can lead to products that are undesired, not giving you all of the desired effect that you wish. So there are other methods that produce Markovnikov additions. These are more desired products and also a lot more straightforward. So oxymercuration, demercuration reactions are what we're going to be talking about today. These reactions avoid carbocations and give you the desired Markovnikov additions. Okay, and they give them to you in a much more straightforward manner. So we want to look at this molecule that helps. Looking at the mercuric acetate, you can see the mercury in the middle and two acetate molecules on each side. And what will happen is that these acids or these acetic molecules would dissociate. The electrons will jump over to one acetic acid and it will depart, giving the negative charge to the acetic acid and then a positive charge to the mercury. This is a very powerful electrophile. The mercury is, or the mercuric cation is. In fact, it's so powerful that they typically will attack the pi bond of an alkene. So let's take a look at what we're talking about here. So here I have an alkene. Okay, I have on all the hydrogens so you can see what it looks like, and I'm going to get rid of those just to clean it up a little bit, and I'll leave that one hydrogen in my second or my third, well, actually my second carbon there. Okay, so we want to kind of trace what happens to that hydrogen. So you see that double bond, okay? So that double bond is electron rich, and these are the electrons that this mercury desires. Okay, it's an electrophile. So it's going to attack that pi bond, and there's going to be a reaction, a bond that's created between that hydrogen, I'm sorry, that mercury. Now you'll notice that the positive charge has shifted over to another of the carbons. Now something very interesting happens here, because typically you'll have that carbocation will create an intermediate where potentially an undesired, some other molecule could attach to that carbocation, leaving you with an undesired product. Okay, so what the mercury does, okay, it'll create a bridge. Okay, think of the mercury as kind of a carbocation babysitter. So what will happen is that it'll create a little bond, a mercurium ion, they call it. Okay, and what happens is that a positive charge gets distributed from that mercury to the other carbon, and not allowing anything to attach to that carbocation. Now you'll notice that the positive charge is distributed. Okay, that keeps it fairly stable, and it prevents carbocations, which you don't want. But it can still be attacked by a nucleophile on the opposite end, on the other end of the molecule, because the other end is just, it's pretty much occupied by that mercurium ion. Okay, and that's exactly what happens. A nucleophile that has a negative charge will be attracted to that positive charge, and it will create a bond. Okay, so now you have a nucleophile that's bonded to that carbon. You're getting closer to that desired effect, but the problem is that we still have the mercury, the mercury ion, okay, the cation attached to our carbon. So this is where you have something called sodium borohydride, and this final step is not typically mentioned, or it's shown in the reactions in textbooks, but it's not really, the mechanism isn't really explained as to how exactly sodium borohydride, which is the typical molecule used to get rid of the mercury, the mechanism of how that happens isn't typically shown. So we're going to just kind of give like a little summary of what happens. You know, typically I found it that sometimes it's mentioned as a magic bond, okay, or reaction, and that's only just a way of saying, just believe that it happened and assume and just kind of move on without actually giving a mechanism. But we're going to give a little bit of a mechanism here so you can kind of get an idea as to what actually does happen. So again, we want to get rid of that mercury that's attached to our carbon, right? So what happens is that sodium borohydride will come in, it will interfere with that bond, okay, and when it does, okay, one of the hydrogens from the sodium borohydride will come in and interfere with that bond, and what it will do is displace the electrons that are binding the acetate to the mercury. So those electrons will then get pushed out and go to the acetate, okay, So the hydrogen comes in. Now again, let me back up. Notice what happens to the NaBH4. It's going to turn into NaBH3, and that's because that one of the hydrogens is displaced into the carbon. Now notice again what happens to the electrons for the acetate. They get pushed up. Acetate detaches, and now my mercury has a hydrogen attached to it, but that's also not a very stable molecule. And you'll notice that there's a lone electron in carbon. That's also not a very desirable position for that carbon to be in. So what's going to end up happening is that that hydrogen that's attached to mercury will then, those electrons will then be shared with the carbon, and a bond will be created with that carbon, completely detaching from the mercury. And you're left with mercury liquid, okay? Because as you know, mercury is the only metal that is in liquid form. So you see all the products that are left behind there. You have the acetate, the mercury, and the sodium with my borohydride with 3 hydrogens, okay? And you'll notice that my alkene, now I have the desired effect, the desired product without any impure molecules that were created by carbocations. So using a oxymercuration reaction avoids carbocations, giving you a more desired product and in a more straightforward manner. Okay, this is a Makarpnikov addition. All right, so let's take a look at the formula as a whole. This is what you end up with. Okay, so you have your alkene on the left. Okay, and then you have your reaction arrow, okay, pointing to the right. And you'll notice that in step 1 you add the meconium, okay, your meconium cation, and then you also add in your nucleophile, which will attach to your alkene, okay. And then thirdly, you want to get rid of that mercury that's attached to our carbon, so you add sodium borohydride. Okay. Well, I hope that was helpful. Thank you for watching, and good luck in your studying.